All right, let's get started. Welcome back. Hope you had a good Thanksgiving break. So we have just a little bit of the semester left now. Here we are, December 2nd. We'll be finishing off the stuff on fast Fourier transform and the short time Fourier transform today. On Wednesday, we'll have a brief look at some of the issues interfacing between discrete time and continuous time, basically the things that happen when we actually do sampling and how we can interpret some of those in the analog domain. Then next Monday, we have our project presentations class. I have 7 groups that have volunteered to give presentations. I'll be sending out an email to those people before Wednesday to confirm and everything. And then that's it for the lectures. Then we have the final exam a week later, and also your project reports are then due on that Monday. And that's the end of the story. Any questions, any issues? Final logistical details? Okay. So let's get on with the slides. So in the last lecture, we introduced the FFT algorithm, which was this approach for calculating the DFT efficiently with fewer multipliers and adds. And it's kind of magic, but it basically, because the DFT normally involves a lot of multiplies by this unit length phasor, which wraps around. They're essentially, that's how I understand it, there are these multiplications which you can factor out, and so you can do it in, rather than using n squared, you can use n log n multiplications to calculate the DFT, which is a huge win as n gets larger. It's closer to being proportional to n rather than going as n squared, which gets increasingly expensive as n gets larger. And this was our final fully optimized 8-point DFT flow graph, where all the actual DFT, the way it works is we divide the n-point DFT into 2 n on 2-point DFTs, then we divide each of those into n on 4-point DFTs, etc. And we end up making all the actual DFT constants disappear, and they just become adds and subtracts. And all that we're left with are these multiplications by these so-called twiddle factors, which are just to sort of combine the even points and the odd points to get the actual full set of DFT points. And we saw that MATLAB implements this, and it is indeed much quicker than using a non-decomposable FFT. You can use radix 2, but you can use any other radix, and you get a corresponding improvement. But if you have a number of points which is a prime number or has only a few factors, then you can't use this trick so efficiently, or you can't use it at all. So we saw some of the differences in speed there. So that basically gives us a box that we can use to calculate a DFT of a particular size, preferably 2 to the n or something, that we can use very efficiently. And because there are many different things you can do with a Fourier transform, this is a function that's very often provided in any kind of library, and is often has a lot of attention paid to optimizing it, because it's, if you care about speed, then you're going to be using the FFT rather than a discrete Fourier transform, and then you want to make it absolutely as fast as possible. So it's often a good choice just because it's provided in a highly optimized form. We talked about how we can have these mixed radix FFTs as well for different sizes. Of course, if we're going to do this whole picture of processing in the Fourier domain, so we're going to take a time domain signal, take its Fourier transform, modify it, take its inverse Fourier transform to get an output again, then we're going to need the inverse DFT as well as the forward DFT. Fortunately, the inverse DFT is almost the same expression as the forward DFT, right? This is the inverse DFT, and the only difference between this and the regular forward DFT is that we flip the sign, we conjugate these constants here, and then we have a scaling constant of 1 over n on the whole thing. That means if we have an algorithm for calculating the forward DFT, we can actually use it to calculate the inverse DFT just by modifying our inputs and outputs slightly. So if we had, this is what we want to calculate for our inverse DFT, but that would be x of n equal to that. Well, if we conjugate both sides, and then we multiply both sides by n to get rid of this 1 over n, right, we get n conjugate x of n would be equal to this, which is now just the regular DFT, but the regular DFT of the conjugate of what we started off with. So this is kind of weird. I'm taking the DFT of the DFT. I'm taking the DFT of the conjugate of the DFT because I've got this algorithm which I assume will calculate the DFT for me. But if I feed in the conjugate here, then I can actually make it calculate the inverse DFT. So here is sort of a way of rewriting this, that x of n is 1 over n times the DFT of x conjugate of k, all conjugated, and that will give me the right answer. And so what that means is if I've got this box here that calculates the DFT, I want to feed in x conjugate of k. So I've got x of k here, and assuming we've got some kind of Cartesian representation where the real and imaginary parts are represented separately, then to get x conjugate of k, I just flip the sign of the imaginary part, multiply this by -1, plug it into my DFT box, get the real imaginary parts out here, and then from the output I scale by 1 over n, and I flip the sign of the imaginary part again to get the conjugate here, and then I get x of n out. So basically, given my DFT block, with just a couple of sign flips and a couple of scaling constants, I get my IDFT block for free, basically. And this is how you'll often see it implemented, that there'll be one routine which calculates the FFT, and then the library will provide an inverse FFT routine, but it'll just be a wrapper around the FFT routine with implementing these few steps. So that's good, that we have a very efficient algorithm for calculating the FFT, and it gives us at the same time an efficient algorithm for going back into the time domain from the DFT domain. The algorithm we've described is, of course, the DFT in general of a sequence will be a complex vector, complex sequence, if you like. It's defined over complex inputs, right? It's all complex math, and so right from the get-go, all of those numbers that we're feeding through our butterfly are complex numbers, and we modify both the real and imaginary parts. Now, very often we may be calculating DFT of signals that are purely real, which is just to say they're complex numbers whose imaginary parts are 0. And that sort of feels a little bit like, gosh, can't we take advantage of that? Because what we know is like at this first stage, if we've got the real and imaginary parts of each value, we know that half of those values are 0. And so we don't really want to do arithmetic operations on them. But after the first stage, when we introduce some twiddle factors, now we do have, even if we start off with only real numbers, we do have some complex numbers in there. So we can't, very quickly we get into complex numbers. We can't take advantage of the fact that we start off with pure real values. And so that seems like, okay, that's an efficiency that we're missing out. The fact is that the algorithm, DFT algorithm we have implemented is capable of handling arbitrary complex sequences, but we're dealing with, we'll very often want to apply it on a highly constrained sequence, which is pure real, which means that the DFT we're going to get out at the far end is going to be conjugate symmetric, because that's the DFT real. That's what a pure real signal looks like in the transform domain. But the FFT algorithm doesn't enforce that conjugate symmetry on the output. It just will calculate whatever it calculates. One way we can maximally exploit the efficiency of the DFT algorithm is to actually pass it a fully unconstrained sequence, a general complex sequence, calculate the unconstrained general complex transform of that, but then build our original sequence by combining two real sequences and then decompose them again at the end. That's what this is about. That if we have two real sequences, x of n, which is our big n point real sequence, and then wn, which is some other big n point real sequence, like maybe it's the next window or something like that, we can calculate a complex sequence as x of n plus j times w of n, right? So these two, this is going to be pure real. Y of n, which is j times w of n, is going to be pure imaginary. So now v of n is complex, and there's no, each point of v of n is independent, and the real imaginary parts are presumably independent or just an arbitrary combination. Okay, so if we've got this complex sequence here, we can take its DFT. DFT is, of course, linear, so it's just the sum of these two, the DFT of these two things. If we conjugate and frequency reverse this DFT, then we're doing the same with these two things here, right? So that, the conjugation is also distributive over addition, and so it's reversing in frequency. But x of k came from a pure real sequence, so x of k is conjugate symmetric, which means that if we flip it and conjugate it, we get x of k again. But y of k was pure imaginary, which means it's conjugate antisymmetric. So if we conjugate it and flip it, then we get minus y of k. So v of k plus v star of minus k is actually just 2x of k. But v of k minus v star of minus k would be, these parts would cancel out, we'd just be left with the y part. So here, given v of k, we can fairly trivially recover x of k and y of k, and then given y of k, we can recover j of k by recover w of k by dividing by j or multiplying by negative j. Same thing. And so we can quickly get the DFTs of both of our real sequences out of this single complex FFT calculation. Yeah?
So what would this be used for?
It just, so why, what's the point? The point is that, I'm counting every cycle. I'm trying to do things as efficiently as possible. Very often, I need to calculate a whole sequence of FFTs of the same size. We'll see that in a second with a short time Fourier transform. So if I've got, m blocks, I can chop each one and run my FFT algorithm m times. Or I can take two successive things, combine them into a single complex sequence like this, calculate that FFT, pull out the individual pieces. And now I've only had to run it m on 2. I've only had to call the FFT routine m on 2 times to calculate each of those m DFTs of pure real sequences. You can see how this kind of process is guaranteed to give you a conjugate symmetric sequence, right? We're taking some arbitrary sequence and then conjugating it and reversing it. So this thing is always going to be conjugate symmetric because, of course, x of k, which is the transform of a pure real sequence, has to be conjugate symmetric. And so that's how we're sort of getting this, getting twice as many values out of one sequence, if you like. So that's, sometimes you'll see that wrapped in a library. You will sometimes see libraries provide an FFT for a pure real sequence. But I'm not sure, you can't do it so efficiently if you don't have pairs of them to calculate, right? So sometimes you need to know about this, you need to apply it at a higher level. Okay. So So picking up on that idea that sometimes we want to calculate sequences of shorter FFTs, let's think about why that might happen. The Fourier domain, the Fourier transform, is a complete alternative to the time axis. That if we take a sequence, in general, the Fourier transform says you can take it over all time, and then you calculate its Fourier transform, and it represents it in terms of frequency components for many different frequencies, which extend over the entire time universe. The assumption is however long your time axis is, either infinity for the DTFT or the n-point finite time axis for the DFT. It's not, but we understand the idea that the Fourier transform is giving us the energy in different frequency bands, the energy in at different frequencies. But we can still think about the idea, well, maybe that energy at a particular frequency is varying with time, a time-varying spectrum. The FFT, or the Fourier transform doesn't really admit that. It says I can either tell you how the signal varies in time, or I can tell you how intense it is at each frequency. But you can't. It doesn't really have this concept of time-varying frequency. But if we have a signal like this, a sinusoid that sort of ramps up and ramps down, an amplitude-modulated sinusoid, then you look at that, and the way you describe it is it's a sinusoid that whose amplitude varies in time. Here's the expression. Here's an expression to give us a sinusoid like that. It's just here's the rapidly varying sinusoid, the carrier in communication terms. Here's the envelope, the modulator, which is now just offset as cosine and offset in time to give us a nice little cycle like that. If we take the Fourier transform of that, basically what we've got is the product of two cosines, right? Which our trig identity says, well, that's just the cosine of the sum and the cosine of the difference. And then there's the offset term. So we end up with if that window we saw before was an exact number of, if we take a DFT of that exact length, then we get something like this with basically three non-zero terms coming out of our DFT, one at the carrier and then two adjacent flanking sinusoids, which are these sum and difference terms here. The sum and difference between the two cosines, right? The carrier and the modulator cosine. So that they're very close to the carrier because they're just spaced apart by the modulator. What that's saying, right? If this is the DFT, if it's only got three non-zero values, that means that x of n is the IDFT of this. It's the sum of these coefficients multiplied by the corresponding complex sinusoids, or if we actually had the DFT which had the positive and negative parts, it would be sums of simple cosines. And so, there are three cosines here now which are defined across all time, or defined across the whole window. They're constant amplitude, because they're regular cosines. And so it's saying that signal we got can be generated as the sum of these three signals. This blue one is the IDFT of this single line here, right? So it's at omega c, has an amplitude of, say 1, n, something like that, 1, I guess, if the DFT is n. And then here's the red line has an IDFT, which is this sinusoid here. It's half the amplitude. It actually, this is the magnitude of x of k. Depending on how we set our time origin, the actual sign of this might be negative. So here, the actual IDFT of this component starts at -1, but it still looks kind of the same. And then here's the IDFT of the green line here. Now, these look like they're all the same frequency, but actually they're slightly different frequencies, right? The red one is slightly lower, and the green one is slightly higher. And so you can see that when we add these up at the time 0, this is 1, this is -0.5, this is -0.5. They're going to add to 0. In the middle here, because this one's going slightly slower, this one is actually half a cycle behind in the middle. So here they're all lined up. So they're going to add up to give us a large value. And at the end, they're out of phase. So they're going to cancel out. So that's basically what's going on. That here they cancel out at the beginning, they reinforce in the middle, and they cancel out at the end. And that gives us the modulated sinusoid. Yeah.
I actually see that there's the blue sine wave.
Yeah.
It's kind of negative in phase with the red and green one.
Yes. Right.
So shouldn't the peak in the Fourier transform be negative, like minus n?
Yeah, that's so. Since it looks like, I mean, again, it depends where your time origin is, but it's like, okay, if we say that if this is just cosine, if this is, x of k cosine k, 2 pi on n, then this one is minus a half, this one's minus a half, and this one's plus a half at time 0. And so the actual Fourier transform would be these things pointing downwards. Now, in general, what I've plotted is the positive frequency half of a complex Fourier transform. So what I've plotted is the magnitude, and so the magnitude makes the negative and positive the same. And in general, they might not even be, they might be some complex value if the phase was not exactly plus or minus 1. So yeah, but here it would not be a bad representation to have them be negative, except that it would suggest that maybe it might tempt you to thinking that we can always plot, the values of a DFT on a real axis, whereas we tend to always plot them as magnitudes, so they should always be positive. So, but anyway, but this way they cancel is kind of surprising. I don't know if you've thought about that before or seen it before, but yeah.
So in the Fourier transform,
Yeah.
so does that peak at which is the end, does it directly represent the amplitude of the sine wave, or does it represent total, a summation of all the energies components present in the whole spectrum?
So what does this peak represent? Does it represent?
Does it give me the direct measure of the amplitude, or it gives the energy present in that tone?
It represents this part, right? If we take away these two flanking parts, which we can do, we can just take the DFT, set those two values to 0, and take the IDFT. This is what we get. I mean, we don't get these two parts. So actually, it has a lower amplitude, right? Because when these reinforce, their total amplitude is going to be 2 in the middle, whereas if we only keep this part, then the maximum amplitude is only 1. But it's sort of like the average, right? Because when we add them together, that goes from 0 to 2 to 0, and so this is kind of like the signal, the carrier signal without the time variation.
No, even if there's a single tone and there's no carrier tone as such, and just by looking at the frequency,
Yeah.
the length of the tone present in that frequency,
Yeah.
can we comment anything about the amplitude of the actual sine wave?
We can.
Exact.
So okay. So here's what's going on. We took a carrier and we multiplied it by a sine wave, right? We took an envelope, we multiplied it by a carrier sine wave. The carrier is the high frequency one in communication speak. If we had a carrier, it has some spectrum down here. When we multiply it by a sine wave, it's modulation, which is a shift in frequency. And so we shifted it up to here, right? And so now this is like the two-sided Fourier transform of our envelope shifted onto where it's centered on this carrier. Now, if the envelope has a DC component, has an average component, a constant component, then that now becomes the energy of the carrier here. If the envelope did not have an average, had a 0 average, we could have had an envelope which didn't have the offset. It was just a cosine modulator. Then this component would have been 0. We would just had the flanking components. And so if you just look at the energy of the middle part, it's telling you what the average amplitude of the modulator of the envelope is, which, often is interesting, but sometimes can be 0. I just wanted to show you this in MATLAB, just to show that it really works. And this is coming from today's MATLAB diary. Oops. or would be if, looks like the network's not working. It's okay, I copied it in already. So I define my sampling rate, I define my time base here as like 16,000 samples at an 8192 hertz sampling rate, so it's 2 seconds worth of sound. And then define 3 cosine functions here as 1,000 hertz, right? 2 pi times 1,000 times t, and then 1,002 hertz and 998 hertz. So this plus or minus 2 hertz. And if we just play those 3 sine tones, sorry, they're 3 1,000 hertz sine tones. They are 0.2% different, right? They're 2 hertz different at 1,000 hertz. No, is that point? So 1% would be 100. 1% would be 10 hertz. So that's 0.2%. That's just sort of normally the limit for sensitivity in frequency difference is about 1%. So they're sort of below the threshold of frequency sensitivity, although our frequency sensitivity is greatest at 1,000 hertz or in that region. So I think you can just about hear the difference. But they sound pretty much like the same frequency, but because they're slightly out of phase, when we add them, if we define y like this, right, as just the 1 minus half the sum of the 2 flanking tones, then you hear now the 2 hertz modulation there. And if we plot that just to see what we're getting, that's our sinusoid with the modulation on top. If we zoom in on this, you can see there is actually a sinusoid in here, but it's just as being, subject to this modulation. If we take its FFT, you see it's this one narrow line, but the narrow line is not a single point. It is, in fact, 3 values. This 1 bin and then these 2 flanking bins coming from these 2, which are the 2 other sinusoids, right? Each of those sinusoid components, because they completed an exact number of cycles in the 16384 points, they have just a single value in at least the real half of the positive frequency half of the FFT, but then if we take all 3 of them, they give us a 3-point DFT. Yeah.
So in this now, the middle tone is at a level of around 8,000. The magnitude of that, is at around 8,000. So what
It
does
is.
exactly signify in terms of the sine wave analysis?
So what is the meaning of this amplitude, right? So the why is it 8,000? It's because the it's if I had an actual complex exponential, right, that was this frequency, but both the real and imaginary parts, e to the j omega n, then its DFT would just be the sum of would be, the DFT of that would be just n, right? So the sum of x times e to the minus j 2 pi k on n times little n times its conjugate would be like the sum of 1 over the entire length of n, big N points. And so the sum would be big N. Because it's a real sinusoid, it's half of the plus frequency plus half the negative frequency. So this is n on 2, because it was a unit amplitude sinusoid. That's what I get here. So that's the n here is 16384, so the actual value of the FFT here is 8192. And then these ones were half amplitude. They had a maximum amplitude of 0.5, so their things are 0.25 of n, which is 4096. but it's proportional to the magnitude. And then the IDFT is the sum of x of k times the e to the j omega n divided by big N. So when we take the IDFT of this, we get a half amplitude of a positive frequency spiral and half a negative, and they add up to give us 1 again. Okay. Yeah?
Is the x-axis representing the actual frequency?
The x-axis here is the bin, right? So it's the bin out of 16,000 bins. The k is n is 16,000, so k goes from 0 to 16383. And the sampling rate here is 16,000, it turns out, so it's actually not quite perfect. But if the sampling rate was 16384, so that the signal was exact. Why is the sampling rate 16,000? I don't know. If the sampling rate was exactly, if the signal was exactly 1 second long, then that would be 16,000 points at 16,000, and the highest bin would correspond to the sampling rate, 16,000. So it would pretty much be hertz. So that's interesting. So what we saw here was that the did I set SR here? I think I meant it to be. I meant SR to be 8192, but somehow somewhere along the line it got halved, doubled. So then, now this sound, sorry, it's going to be loud. So that's 1 kilohertz. And then when we play this thing, right, so that's 2 hertz modulation, 2 seconds long, so there were 4 cycles. We heard it like played twice as fast before. Now, when we plot the FFT, this is actually 8 kilohertz, or 8192, because this is the full DFT from 0 to k, so it goes all the way from 0 to 2 pi, and 2 pi corresponds to the sampling rate. So this is actually 8 kilohertz, so now this here, which is the Nyquist limit, is 4 kilohertz, is the 8,000th point is 4,000 hertz, and so now this 2,000th point is 1,000 hertz, which is what we designed it to be. I'm sorry, I managed to make that sound more complicated than it is before, but remember that thing we had where we said that the omega which is the discrete the normalized frequency, it's called the discrete time frequency, which is in rads per sample. Right, that's what it means. It's how far the vector advances every sample is equal to omega, the big omega, the discrete time frequency, which is in radians per second. And then to make this work, we're going to have to multiply by seconds and divide by samples. So we have times t, which is the sampling interval, which is seconds per sample, or equivalently, right? So that makes the units work. Equivalently, we can divide it by fs, which is the number of samples per second, right? And then seconds cancel out, and we get radians per sample at the end. So it's just proportional, like that. Okay.
But wait a sec. So,
Yeah.
so that 2,000 though, so you want to write the FS, what's your FS again?
My FS now is 8192, right? I can just change it if I want and play it out at a different frequency. But here, so I plotted this, the abs of FFT of y. If I plotted it, I can give a first argument here as the actual values, the x-axis values, and I can make that 1 to length y. Times the sampling rate divided by length y. So now instead of going from 1 to 1 to 16384, it goes from 0 to 16383. It's divided by 16384 and then multiplied by the sampling rate. So now it goes up to 8192, and now the actual labeling here is the actual frequency in hertz, right? Which is right around 1000. So you see it's like 998, 1000, 1002, which were the frequencies that we actually put into the sinusoid calculation. If you look at the, I can't bring it up right now, but if you look at the MATLAB script from this week, I think that's one of the examples, is actually getting the frequency axis right. Okay. It's worth paying attention to that, right? Because that's kind of, when we take these FFTs, we want to relate it to the real world. We want to know what these actual frequencies are. And so it's a little bit, it's a little bit unobvious. Yeah.
We've been over this several times, but again, so the amplitude.
Yeah. Yeah.
So that corresponds directly to the. Yeah, you can translate that to the actual amplitude of the signal, right?
Right. So the amplitude here, so I'm managing to make this a little bit confusing because we've got the same number showing up in different times, meaning different things, right? But here, if I take an endpoint sinusoid and calculate its DFT, which is the inner product against the conjugate endpoint sinusoid, then if it's fully conjugate, then each point in my endpoint sum will be 1, and so the total sum is n. So the DFT, the way we define it sort of depends how you define it, but the way we define it, the DFT of a unit amplitude sinusoid has magnitude n, or if it's real, it'll be n on 2 here and n on 2 at negative frequency. And then the IDFT of that, if I have this thing which has magnitudes, values of n on 2, positive and negative frequency, take the IDFT out, I'm going to get a unit amplitude sinusoid. That's what it means. But it's all proportional. So if I scale the first sinusoid by k, or by alpha, now the values of my DFTs are going to be alpha times n. But it'll still, and if I scale something in here by beta, then when I take the IDFT, the magnitude is scaled by beta. That's linearity. Okay. All right, so here, why are we doing all this? Oh, yeah. We've got this amplitude modulated sinusoid. We can take its DFT, no problem. We get this little, we can think of this as like, well, it would be a single tone, but the amplitude modulation spread the frequency a little bit. Another way of thinking of this is like, it's like our tapered window. Our tapered window, to gain the smoothness of the edges, we gave up a little bit of frequency resolution. So this has broadened our blurred our frequency representation of the sinusoid a little bit by that window. But what we said was, well, what that signal really looks like, and what it sounds like, is a sinusoid whose amplitude is varying. A sinusoid with a single frequency, not 3 sinusoids added together. 1 sinusoid, but an amplitude that's varying. Something like this, A of n cosine omega 0 n, where A of n is time varying, but time varying on a much slower scale, right? So it's, in general, if I'm just saying, well, this thing is the product of 2 other sequences and I don't constrain them, then there are lots of different sequences you can put together to multiply to give you something like this. But if you say, well, this one has to be slowly varying, it doesn't have to be constant, but it can't change too fast, then you can then you get something close to a well-defined sequence. It's actually quite difficult to define this in a way that really is completely satisfying. But that's kind of what it sounds like, right? How can we get this kind of representation out from our Fourier transform? Well, one thing we could do is rather than taking a Fourier transform of the whole thing, we can chop the sequence up into shorter subsequences, each describing what happens around a certain point in time, and take the Fourier transform of those. And then if our modulator is slow, and if our short subsequences are short enough that it hasn't changed much over that window, then we can sort of treat it as constant within each short window, and then we should be able to see the variation of this constant scaling through our evolution of our successive short windows. So here is what I'm talking about. We have our long modulated carrier here. But instead of taking a single FFT of the whole thing, we're going to chop it up into, in this case, 8 shorter sequences and take the Fourier transform each one of those. And so we end up with 8 individual Fourier transforms here. So if this original sequence was 1,024 points long, then when we divide it up, we're going to get 8 128-point sequences. When we take their DFT, we're going to get 128-point DFTs, but including both positive and negative frequencies. So we just put in the positive frequency, we're going to have the 64 frequency bins. And then here we see there's one bin, which is our carrier, and the amplitude grows, because in here there's a little bit of energy at this frequency, but it's pretty small. It's also got this modulation, right, this linear modulation. And so you can't really see it, but this thing is not quite aligned. It's got a little bit of spread, because there's some modulation here, but it's not sinusoidal. And then here the amplitude is larger, so this thing gets bigger. Here it's larger still. And we get this sequence of values for this bin at the carrier, which go up and down in amplitude, which is kind of what we're trying to get to, this description of the frequency as amplitude modulated. Yeah.
So each of those 120 intervals,
Yeah.
so that has actually got the main frequency tone, which corresponds to that,
Yeah.
which it shows.
Yeah.
Also, but doesn't it show the modulation component as well?
Yes. It shows some modulation. You can't really see it here, but if you look in here, you can see there's a little bit of white in here, because there's some kind of shape underneath, which is, so here's this thing. It's basically looks pretty much like a linear growth to the underlying sinusoid. And when you do that, that gives you a Fourier transform. It's, to build this linear amplitude out of sinusoids, you have to, you can do it.
It's not a single tone in that case. It has a
Right. Right.
multiple tones.
It's not a single frequency component. It's the sum of a number, right? Actually, probably has non-zero Fourier transforms for many harmonics. But most of them are pretty small amplitude. The only large amplitude one is the carrier, and then there's a little bit of, to build this out of the Fourier transform, it adds in some other sinusoids at slightly different frequencies to cancel out, but they're much lower amplitudes. So I have this one peak at the carrier, which is what we're looking at. Yeah?
Is there a reason why you choose 8 instead of any other number?
No, the 8 is arbitrary here, but there is a trade-off. Right? If I'd only chosen 2 windows, then I would have taken the Fourier transform with this half and the Fourier transform with this half. I would only have 2 time samples of my amplitude. They would have been the same. I wouldn't have been able to see the detail of the envelope modulating. So I have to choose the windows short enough so I can see the energy variation that I care about. But if I make them really short, then maybe I wouldn't even be able to get. I would get fewer and fewer bins here, and I maybe wouldn't even be able to see the carrier. So the shorter I make them, the less frequency resolution I have, because I'm looking over a shorter window. And so you don't want to make them too short, because then they become meaningless. We'll see that. But that's.
Is there an optimal way of choosing this?
Is there an optimal way of choosing it? Basically, no. But then, of course, optimal means, well, what are you trying to optimize? You define something that you want to, some optimization criteria, and then of course, yes, there's some choice of n which will give you the largest value for your optimization criteria. So, but there's no sort of universal way of deciding what the right window length is. It depends on the structure, the nature of your signals. It depends on your domain, what you think, how much time structure you want to be able to see, and how much frequency structure you want to see. We'll see this in a second, in more detail. This trade-off. Yeah.
So interpreting the figure, let's say, so in this case, would 1024 correspond to my sampling frequency, or would 128 correspond to the actual sampling frequency of the signal?
So how do these numbers correspond to the sampling frequency? The sampling frequency is completely, it's just whatever it is, right? I've got a sequence of 1,024 points here, at this point, I don't know what the sampling frequency was. Doesn't matter. I mean, it's sort of, all that matters is if I plot these, when I plot these FFTs, when I plot these DFTs, now the index here is in terms of k, the DFT index. If I wanted to plot that in terms of hertz, some frequency, some real frequency, then I'd have to know, what my sampling frequency was, so I could do the scaling. But note that this is a 128-point DFT at the original sampling rate. So now this 64 goes up to the Nyquist rate. Like if I plotted all 128 points, it would go up to the sampling rate. So 64 goes up to Nyquist, and so this is whatever it is, bin 4 or something is 4 128ths times the sampling rate is the actual frequency it corresponds to. All right. Let's just follow this through and see what happens. So now we've got something which is actually close to what we want. It's telling us where the energy is in frequency. It's saying, well, it's on some bin on this DFT axis, and it's showing us how it varies in time. Starts off small, then grows, and then fades back out again. But it's a little clumsy to look at all these successive values of the spectrum, particularly if there are a lot of them. So instead, we try and plot them as an image, where we take each one of these slices and then we convert it into a set of pixels, and then make the value of the DFT into the reflected by the color of the pixel. And so now, here are our 64 bins or whatever, and here are the colors, and then most of them are white, but here, this bin is getting large, we make it go dark. I've plotted, this is my mapping here. And now we have this picture where we've got time going in this direction, we've got frequency going in this direction, and then we've got the color telling us how much intensity, how much energy there is at each frequency as a function of time. And this image, notice that this is just the magnitude of the spectrum, so I've lost the phase information, but this image is called the spectrogram. And it's this, we've seen it a few times as a way of looking at the time-varying spectral content of a signal. And we can sort of try and formalize what we've calculated by defining a function of two indices, a frequency index and a time index, and which is what we just had. And it's called, when we do this, it's called the short-time Fourier transform. And when we plot the magnitude of the short-time Fourier transform, that's what the spectrogram is. So the short-time Fourier transform here, it's got a frequency and time indices. There's no fixed convention about exactly what they're going to be or what order they occur in. This is kind of backwards because it's like I've got the y-axis and the x-axis here, but it's because we're used to thinking of x of k, and so now we're adding an extra time variable here, which I put them in that order. So x of k would just be the sum of x of n times e to the minus j, whatever, 2 pi kn on big N. So x of k and n0, we offset x by n0, by the time here, and then we have a window here. We might have had that for our regular DFT, just a tapered window to give us some time localization. But now we assume that x is much longer than our big N Fourier transform points. And so we sort of need this window to limit it just to the big N points. We don't actually need it because we're only summing over those points, but by having some window in here, we can sort of assume that we're summing over all x, but now we've got some window to localize it. And as we vary n0, we're going to get different chunks of x falling into this window, giving us different samples of the signal at different times. Yeah?
But this equation implies almost perfect overlap of the windows and the time chunks.
Yeah.
But what we did in previous examples, we took really individual chunks of the time scale.
Yeah.
So it's not exactly the same, but they could be the same.
Right, so the question is, in the previous example, what we did is we chopped up x into some number of pieces, and each piece was non-overlap, was distinct, right? There was no overlap. This thing, actually, this time index here is not, in the previous example, n0 wouldn't be 0, 1, 2, 3, 4, 5, 6, 7. It would be 0, 128, 256, right? This is actually in the units of the original time base. We could have calculated it for 1. Instead of having the second block be this, we could have shifted this window over by 1 sample and done the whole thing over, but just for sample one thing over. So rather than having 8 of these things, we could have actually had 1,024 of these individual short spectra, and they would have sort of been the interpolation between these ones, right? They would have all looked more or less, the next one would have looked more or less the same. By the time we got to here, it would look like this. So we would have had a lot more points. And all that would have happened then is instead of having these very broad pixels here, we could have actually had more pixels that would have nicely smoothed out this variation in the gradient here. Because of most of the points would be the same, there's a strong limit on how rapidly this thing can vary. So we wouldn't actually be getting more information, but we'd be getting a nicer picture of the same information, basically. It's kind of like zero padding in the DFT.
So practically, there's no problem. There's no limit on the overlap of the windows.
Right. Well, there's no.
You will experience some problems only on the length of the chunks, not on the number of the chunks.
Right. Okay. Right now, I've just defined a function which I can calculate at any. I mean, I can calculate it if you like for any single frequency for any single time point. You know, normally when we're talking about the DFT, we think about calculating all the frequencies, but now we can just choose a particular time and calculate it. Short time Fourier transform just means it's the Fourier transform over some short, limited time window, some local time support. Now, as we've seen in the spectrogram, we want to calculate this at multiple times. But what times should we choose? We could choose the times so that the windows just touch each other, they just abut. We could choose the times more finely than that, so the windows have overlap. And we'll see that's what we actually normally want to do. We could choose it so the windows have gaps in between. You know, right? So there's a chunk of X in here that never falls into any of our windows. Now, what would happen would be if something happened in the signal in X, it would not be reflected in our spectrogram. So that would be kind of undersampled. We'd get some information loss. But mathematically, we can still calculate it. The issue comes if we want to try and reconstruct the signal. If we want to take X of Kn and then get back to little x, then we're going to make if we have gaps, then we're going to have big problems. And if we have overlap, then we have a few issues, but we'll see that they're not too bad. So normally, if we want to have a complete representation, meaning one that we can reconstruct from, then we want to make sure that our windows at least touch and usually overlap. We'll talk about that in a second. Okay, so now we understand what the short-time Fourier transform definition here is. Yeah?
So correlating this with the one previous statement, Windows.
Yeah.
Can we? So can we use visualize this as having one FFT engine with 128 points?
Yeah.
And it continuously keeps updating its FFT bin as and when the signal progresses.
Yeah.
So basically, for the first, so if we have only one FFT engine with 128 points, and we pass the signal to that.
Yeah.
So for the first 128 points, it shows the leftmost.
Yeah.
And then it updates itself to the next. So it's kind of streaming.
Yeah.
Algorithm.
Yeah. So what we're saying is that this. You can imagine this thing which takes a chunk of a buffer's worth of X and calculates the DFT and plots the result. And then maybe the sample clock moves on. So now, basically N0 goes from 0 to 1. Now we've got a different window of 128 points in our buffer. We calculate DFT again, and we get another value out. And that would be this value, just here, the next one along. It would be very, very similar because all the points except for 1 in the buffer would be the same, although they're all shifted over by 1, so actually the linear phase would shift, but the magnitude would stay pretty much the same. And then you could keep doing that. What we've actually done here is we've sort of run the FFT routine on the first buffer, but then we didn't do it for the next 128 samples. We let the buffer slide through, and then 128 samples later, we ran the FFT again, and we got this one here. But we could have done it, say, 64 points later, or we could have done it any number of times. And all that's doing is choosing the values of n0 that we actually use to evaluate this thing at. Okay. So here's this issue about the window shape. If I, so there was this Wn in the equation, which is basically scales the particular values, the subrange, the values of x that I take out. And if I just take it as a rectangular window, then I'm basically just keeping those values without any scaling. But we're taking the Fourier transform of a window time domain signal. If we think about that x of k and n as the samples from a DTFT, x of e to the j omega and n, then it's the DTFT is this shifted, it's the DTFT of the shifted version of x and this window function, which means that its DTFT is going to be the convolution of the shifted version of x and the window function, which means that, you know, all the structure in here is going to be blurred by this window function. Notice also that this thing is a shift in time, which in the DTFT domain is just this linear phase term here, right? It's just, I mean, this is, theta is our frequency variable for this. But it's a phase shift for every frequency bin, which is proportional to the amount of the time point we're looking at, multiplied by the full DTFT of the full x of n. That's kind of weird, right? That we actually take here, we're calculating these spectra local in time, spectra that only look at a certain chunk of the signal around n0. But where we get it is by taking this integral of the spectrum of the thing for overall time. It's a DTFT, so it's, you know, it's infinitely dense in frequency. That thing convolve with this window function with this linear phase term. The reason that that's weird is that as I vary n0, I'm effectively looking at different parts of x of n, the time domain signal. I'm moving my time window around. But I'm still doing this integral over all frequencies with the spectrum of the full signal. But by changing this linear phase term, I essentially cancel out the information from all parts of time except for the time within a certain window. Sort of, it makes sense that blurring, it makes sense to me, maybe, that blurring with time is going to take this very, very fine spectrum and smooth it out so it only refers to a relatively short time window. What's kind of harder for me to get my head around is the idea that the actual point at which the part we're keeping depends just on this linear phase term, so which is like a twist, right? It's like twisting the spectrum because we're just adding this phase, which depends on varies with frequency. So we take the original spectrum, we twist it up, we smooth it out by convolving it with this window function, and that gives us the DTFT of the signal at a particular point in time. But that's what it comes down to. Yeah.
Can you just explain
Yeah. This is not a. This is kind of. I want to mention this because we've got the tool to think about it, but it's not important. But what? Okay. The DTFT around a particular point is just the if we have a window function which is 0 except in this part in the middle, we can take our x function, which is arbitrarily long. We shift it so the part we care about is around 0. We apply this window, so we only keep that part that we care about. Everything else is 0. We take the DTFT of that, and that gives us our thing that we're sampling when we get x of kn. By using our DTFT identities, that corresponds to the multiplication of these two signals, so it's the convolution of these two in frequency, right? Assuming that we've got the Fourier transform, then the DTFT of the product of two time domain signals is the convolution of their DTFTs. But this shift in n here is just taking x of n, but we're shifting it, so we multiply it by e to the j omega n0, right? It's called theta here because it's the integral variable. And so the process of multiplying these two things in time is basically convolving the spectrum with this Fourier transform with a window function. It's like smoothing the spectrum with this. Window functions typically look like bumps in the transform domain, so just smoothing it out, taking like a weighted local moving average. But and it's for the whole signal, but the only way that we decide which part of the signal we're looking at, which n0, is by first taking the signal, applying this linear phase term, which is like taking the spectrum and twisting it, applying a linear phase so that, the further along it is in frequency, the more it gets twisted. Just doing that first and then smoothing it out. There's more I could say about that, but, it's just like, I just want to mention that so that if you have time and if you're curious, you can think about it on your own. I think that's probably the best way to handle it. Okay. But the point about going through this is like, well, what are we going to use for our window function? What can we do with our window function? So if we started off with a signal that was just a straight sinusoid, if we have a window function, which is, say, a rectangular window, its Fourier transform is this periodic sink, this 1 over n dying away thing, then the thing we get out is this. This is our x of k n0, which is going to have this nice narrow line turn into this sort of blurry thing with these ripply side lobes. And this is exactly what we saw with the ideal finite FIR filter derivation, that these things are probably not what we want, right? These things look like structure, but they're not structure. They're just artifacts that come from our window. And so instead of using a rectangular window, maybe we want to use a tapered window, like in this case the Hemming window, which was like a raised cosine, a cosine with a little bit of a pedestal under it, which then has this Fourier transform, which has maybe a fairly broad main lobe, but the side lobes are much lower in amplitude, so we don't get these weird kind of ghosting ripples coming out the side. The other thing, of course, is that we can vary the length of that window, right? Regardless of its shape, we can make it longer or shorter. And that's going to have a corresponding impact on what happens to our spectrum that we're sampling from. If we have a short window, then it has basically there's this reciprocal relationship that as we make the window shorter, it's still whatever it is, a raised cosine or a sinc function. But as we get it shorter in time, it gets longer in frequency. So here's one window in time, and here's its shape in frequency, which is this nice, it's this shape, this bump here with these side lobes, but the side lobes are very low. If we make it longer in time, and we can make it shorter in frequency, which means that we're getting better frequency resolution. If we look at that up here, what that's saying is if the window is fairly short, we don't really have a lot of, if we've got the signal which is periodic, we can't really see the periodicity within each window, right? The window isn't really long enough to see the repetitions, these successive peaks. And so basically, we don't even have enough information to know that there are these harmonics from this periodic signal. Here, with this longer window, the Fourier transform can notice that there's this periodicity. It'll start giving us harmonics. And so it's like, because this longer window has this narrower transform, when we blur with this narrow blurring function, we're able to preserve the individual spectral detail. When we blur with this broader function, then all that spectral detail gets washed out. And so we have this is kind of, now we see what the issues of choosing the window length are. The window length in time firstly dictates our time resolution. With this long window here, we can't see short-term variations in the amplitude here. But it does give us extra frequency resolution, so instead of seeing this variation in time, we can see it in frequency. And then depending on which one of those is the natural one we want to achieve with our in our application, that'll dictate the kind of window we want to use. You can think about these different lengths of time window, on a sort of time frequency plane. That basically, if I have a short window in time, it's going to have a broad for a transform, a broad bump in Fourier transform. If I have a longer window in time, it's going to have a narrower bump in a Fourier transform. If I sort of plot these as, the marginals of some image here, we get a series of different shapes here. And basically, because there's this reciprocal relationship, the total area of that bump remains constant. But I can either squeeze my blurring bump to be narrow in time, which makes it broad in frequency, and then basically smooth my entire time-frequency plane with this to get good time resolution but poor frequency resolution. Or I can do this, have good frequency resolution but poor time resolution, or I can have any compromise in between. And basically, it's an instance of the uncertainty principle, which is the resolution in frequency, the product of the frequency resolution and the time resolution is lower bounded by some constant here. It's not the it's the same math as the uncertainty principle in quantum physics. Another way of understanding this is that we've got this time-frequency plane, and we can chop it up into a certain number of tiles, but the shape of the tiles can be varied. The total number of tiles is the amount of information that we can represent is finite, but we can shape it in different ways to trade off time and frequency resolution. Yeah.
So this SPFT window thing, how's it different, or is it different from like getting a signal, chopping that signal itself into different slices?
Yeah.
And taking the DFT of the individual slices.
Yeah.
No,
so we started off by saying, well, we're going to chop the signal up into individual chunks and then take the DFT of each of those and plot that. And this is the same thing, but just now by recognizing that we can have overlaps between those slices, so we don't have to have, it's not like you're either in slice 1 or you're in slice 2. It's like, okay, we can take slices from, we're just going to take a chunk of 128 points starting from some point in the signal, so we can have any of those. And then by taking different lengths of those chunks, we can get different amounts of frequency resolution. Now, obviously, if I've got a tiling like this, which corresponds to quite a large number of frequency samples, but relatively infrequently spaced, it means I've got a fairly long window. I could calculate it halfway along, so I could get, I could draw 2 sets of pixels here, but it would just be interpolating. There wouldn't be extra information available because the overlap. Basically, even if I just took this, with an ideal interpolation between these points, I could reconstruct what that bin was going to give me from halfway along. So it's just smoothing out your picture. Let me just get to I've got a demonstration coming up where we actually vary the window length, with a slider, which I think will make some of these effects clearer. Let's just set it up first. Okay, so we took the spectrogram we said was taking individual short windows, taking those FFT bins, and then plotting them as colors as a set of narrow slices, narrow pixels, and then drawing those all together. When you look at it on this kind of time resolution, you can see the individual FFTs, and it's kind of obvious what's going on. When you zoom out in time, so these things become narrower, then you get this picture here. So this is exactly this chunk in here, right? Here's this white stripe here. But now, just because the time axis is compressed, we can't really see the individual pixels in time or frequency. It looks basically like a continuous image, and we could interpolate the points to make it actually a continuous image. But this is the spectrogram that we're just looking at, and this is an extremely insightful and, as far as these things go, intuitive representation for the sound. You can see that there's, the dark parts are where there's times where there is some sound energy, and then you can see these contours, which correspond in this case to the formants, the resonances, the vocal tract, changing in time. And so this is what we normally think of as a spectrogram. So here's a single piece of speech. Here are 2 spectrograms. This one's with a 256-point window, and this one's with a 48-point window. And they sort of look the same, and here's the energy in this point. But they also look kind of different in that in this spectrogram, we can see these horizontal structures, which are the individual harmonics of the pitch of the voice in here. We can see this, near periodic variation in the amplitude, which is because it's some oscillation of the vocal folds. And we can see the set of harmonics. Here, with a shorter time window, the structure and frequency is lost. We don't see the harmonics, but we see the individual pulses here showing up as vertical structures, the individual maxima in the time waveform here. And again, you know, depending on what you want, you can go for either of those. So again, in the diary, I use this neat little this function I got off the MATLAB file exchange site, which will allow you to like take an arbitrary function and then control it with a slider to get different values out. Where is it? Sorry. Okay. So it's this func slider. You give it an arbitrary function, you know, an anonymous function here, and you can see on the diary how it works, how to make it work. But now basically I can slide this thing along, and now as I move this, it's replotting the entire spectrogram, but with a different window length, where I put my slider is determining the window length. So over here I've got a long window. It's like, I think it's proportions. It takes this number and multiplies it by 1024, and that's the window length. So here with a long window, you can see we've got this very nice display with all these clear, well-defined harmonics. So here the pitch of the voice is dropping slightly. If I play you that speech, that signal, yeah, right. That's why the sampling rate was higher, because I've been doing that. Whoa, what happened there? Oh, well, I think you've heard the speech before. You know what it does. Oops. So here, it's like he's saying the football. I don't know. It's like watch. So you hear the pitch dropping. You can see these harmonics falling here. Now, as I make it short, if I make the window shorter, it doesn't change that much. If you look at, you know, these rapid transitions here, as I make the window shorter, you can see that this has been blurred out slightly, right? Slightly wide in time, but probably it's a very short burst. And as I make the window shorter, that blurring, that picture there, that image there becomes narrower, because that's basically the window where that little burst of energy gets into the spectrogram. Okay, here we've still got the harmonics showing up. Looks pretty much the same. But then around here, things start getting a little bit different, right? The harmonics begin to become unclear, and then we can see this vertical structure, which is the actual pitch cycles. And as we get down here, now the harmonics we can't see anymore, but we can see these individual vertical things coming from the individual pitch cycles. And if you look at these ridges here, these sort of bands of orange, right out here, you can sort of see this band of orange, but it's basically because these adjacent stripes are all kind of orange in the same region. As we shorten the window, we're blurring out the resolution on the vertical axis, on the frequency axis, and these orange things are all merging together, and now we have these well-defined single resonances, which are the actual formats merging together. So you sort of see, and then if we go right down, it becomes extremely broad, and you know, we can't even see these individual resonances picking out too well. But in this region, from here through to here, we have this transition from, you know, time pulses to frequency harmonics, which is, you know, the depending on what you want to see, you might choose different values in that. Any questions about that? All right, so the spectrogram is probably something that you might find useful in your project, so hopefully I've introduced you to that. In MATLAB, you know, this is actually the how you do it. I use spectrogram. Spectrogram is now deprecated, but I still use it. Basically, you use the time waveform, the FFT length, which by default is also the length it uses 50% overlapped Hamming or Han windows, and if you use sampling rate, then it plots with time, does time and frequency labeling for you, so you actually get the real time in seconds and frequency in hertz. It plots, the plot it makes is on a log scale, on a dB scale, so you have to be careful to use a color bar that actually gives you a sensible range. More than 80 dB of range is kind of too much. That's sort of, you know, as much as you would care about for sound anyway. but it'll auto-scale, so sometimes it'll give you like 300 dB range. So you want to make sure that you control that, and then to make the plot fully described, you should use color bar to make sure that you have those things up here. All right. Any questions? Okay, so we'll just talk about this briefly on Wednesday, then we'll talk about the continuous time stuff. I'll see you on Wednesday.